All right. Well, thank you for the very nice introduction. One thing you forgot to mention, which I actually didn't tell anybody, I'm also splitting my time between Apple and UT right now. Now, this talk has nothing to do with Apple. Just if Apple lawyers are listening, this is all UT work. Okay. One more thing. I was a postdoc at Berkeley right before Fisher was a postdoc at Berkeley. So we definitely have very much the same influences and the same sort of ideas on how to approach problems and what problems we like. Yes, and we both worked with LaVILA before that, yes. Yeah. All right, so let's get started. Today I wanted to talk about how vision or autonomous vision is actually changing. And if we look at sort of the field of computer vision, we have been lucky that a few times we have been challenged. Sort of in the 90s, we did a lot of geometry, and then data sets came along and recognition was rising. And sort of that was a really refreshing change in the way we tackle problems. Then in the 2010s, deep networks came along, and again, everything sort of changed. And I'm going to argue in this talk that we're in a very similar moment right now. And in fact, the two things that we had previously are both about to change. All right. We're going to think about data sets slightly differently, and we're probably going to think about the way we handle or we deal with deep networks a little bit different. Right. And the changes are obviously A, large language models, and B, which is maybe a little bit less obvious, the transformer architecture. And I'm going to show you how the transformer architecture actually allows us to do things that we couldn't do before. All right. But first we'll look at large language models. All right. And I'm going to argue that the large language models are actually going to be the end of categories. Sort of we curated beautiful data sets with beautiful categories over the last 20 years. And I'm going to argue that this is going to end. And sort of we're not going to do a vision like this where we select sort of a few classes that we really care about and ignore vision for everything else. All right. I think what's about to change with large language models is that we actually do a vision for everything. All right, for everything that we can put words to. All right. Now, obviously, sort of one of the first changes in this direction was CLIP. And so what CLIP does is it trains an image classifier, but instead of classifying images into the 1,000 or the 21,000 categories that we have in ImageNet, now it classifies images into anything you can put a word to. And the way this works is that we're going to learn an image classifier. This is the same architecture as we used before, but we're now also going to learn an encoder for text. So we're going to learn a language model that encodes text into some feature, some embedding. And now we're just going to say, instead of predicting labels for the image model, now we're just going to put text and images together in the same embedding space. And so if they're similar, if they occur together, we say, good, you should have similar embeddings. If it doesn't match, we'll have different embeddings. And so we're going to optimize a loss that simply just tries to put an image together with text on a large data set of matching text and image pairs. Right? And so under the hood, actually, training not much change. The biggest change was that we now, instead of using sort of fixed categories and labels and having features associated to them, we're now just encoding everything with the English language description of these labels and text descriptions. Now, it turns out that people in object detection were actually thinking about this way before CLIP came out. So if you look at the way a classical detector works, is you're going to have some backbone, and then after that backbone, you're going to extract boxes and you associate feature to these boxes. And in a classical detector, the very last layer has sort of one set of weights associated to each category in that detector. Now we can replace this with a word embedding. This actually has been done in 2018. So way before CLIP was cool, this was done in object detection, right? So now we're going to take the English language, sort of the English language, the words that are associated with the class, and we embed them. And we're going to build a detector that now could, in theory, reason about an arbitrary set of classes. right? Now, the issue here is that we don't actually have a very good training set for these detectors. Our detection data sets all are just sort of labels. They have like fixed categories. So one way out of this, and Fisher already alluded to the solution in his talk, is to actually just use clip word embeddings. And so that way we have a good embedding for text. And then we can also use the clip encoder to ask, hey, if you had to classify this image back here, if you had to classify this image, what encoding would you produce? And then we can supervise the detector that way. Now, there's one sort of technical issue with this, which is the images that Clip was trained on don't actually look very similar to the images that the detector produces here. And so while this idea works quite well, it is a little bit limited in the way it can generalize. Now, in some work that for the generalization, here's an example. Here's a simple baseline that we actually trained along this method. And we fed it lions in the end. So we fed it in images of lions. And for the first image, it just thought it was a dog. The second image, it thought it was a cow. The third image, it was a pony. And the fourth image was a bear. Right? And so what happened here? Well, Clip actually never quite saw images that were sort of tight boxes. So it didn't know what to do. And then the detection data sets we had to fine-tune our detector, even though it could reason about our arbitrary classes, the detection data sets didn't have a lot of images of lions. All right. And so the detector went back to the things it knew, which were sort of dogs, ponies, cows, where it had a lot more labels. Right? That's sort of an issue, right? Because now we have this detector that could reason over an arbitrary set of classes, over anything we could put words to, but we don't have an extremely good way to train it. Right? Now, in some work at ECCV last year, we showed a way forward on how to train this on much larger data. And the detector that we chose here is we used the clip embedding to embed all our words, but then we trained the detector completely from scratch. So we didn't use the image embeddings of Clip at all. We tried to train this completely from scratch. Now the question is, what supervision did we use to train it? Well, for anything that we have annotated boxes for, we'll just use the detection annotations, right? So we'll use Coco and Elvis detection annotations. And for that, we supervise the detector both using the bounding box location and the class label. All right. Now, we can also get data that doesn't have bounding box information in it, but has lots of class labels, and we used ImageNet 21K for that. Now, the question is, how do we supervise a detector if we don't have bounding boxes annotated? And the solution we came up was embarrassingly simple. It was so embarrassingly simple that the first time the paper was rejected. So, yeah. The solution really was to ask the detector to detect all objects in an image. So let's say this is the image, and we'll look at all the possible detection boxes that we can find. And let's draw one more here. And now we're just going to say, well, we're going to take the largest box that the detector thinks is good. We associate the label that was previously associated to just the image to that largest box, and we hit the training button. All right. Now, one key component here is that we do not supervise the location of this box. All right. So we do not supervise the bounding box regression of this box. We only supervise the classifier. And so that way, it doesn't really mess up the detection ability of the detector, but it sort of massively improves the classification ability of the detector. Right? And this is the result. So we put the demo out, and some people on Twitter started to just enter sort of arbitrary text descriptions of what they might think is in the image in front of them, and the detector is just able to handle all these words, these tags. Here's another one. And this is our image from Alyosha's office, where we initially sort of Alyosha actually challenged me sort of right around the time when Fisher joined to detect all objects in there, and we can finally do it. Now, we cannot do it with categories. We can do it with just language descriptions of all the objects. All right. But this also works quite well on the, so this is the Elvis Open Vocabulary Benchmark. We can sort of show that if we didn't see classes, so this is sort of zero-shot generalization to concepts that were not in the data set before, that we didn't train on and just evaluate on, we can see a huge boost in performance compared to the model that actually did not have this image level supervision, right? So these are classes that were neither in ImageNet nor in the detection training data set that we had before. And we see quite a boost. And these are classes that we trained on. And again, there's a slight boost just because we have more supervision. All right. And the next thing we started doing is we started extending this to video. Now we don't do detection. We actually go back to the standard classification setup, just like a clip. And we wanted to see, can we learn a clip-like model that is able to handle videos as inputs? And down here, this should be video encoder. And so what we're going to do is we're going to learn a model that looks at the video clip, that embeds it into a fixed size feature, vector. Then we have a text encoder. This is very much the same model as clip, and it also embeds it in a fixed size feature vector. Now, the issue with videos is that the amount of supervision that we get for videos is very sparse. So if you look at sort of how many clips over a long video are annotated with sentences, they're both temporally sparse, and then the clips themselves, this is just one possible explanation to what's going on in the video. Now, they're sparse primarily because it's actually quite expensive to pay users to annotate videos densely. Now, our solution here was to simply just use a language model, use a large language model to interpolate and create a lot more annotations. And so there's two ways we do this. One is we're going to look at all the human annotations, and we're just going to paraphrase them. We're going to ask a large language model, hey, how else could you write this sentence? All right. The second thing we're doing is we're looking at the annotations that were provided by humans, and now we're asking a large language model to complete these annotations. So we'll give it the first and the last sentence in a paragraph, and we'll ask it, hey, write an entire paragraph in between. And now we have text labels for every single clip in between. Now, there's some alignment that needs to happen in the model, but after that, we sort of have much denser annotations. And then we trained the large vision language model the same way we would have trained a clip. And this works surprisingly well. So what I'm showing you here is a bunch of video data sets, and we're comparing our method, zero-shot, to these new data sets, to the state-of-the-art zero-shot evaluation on these data sets. So this is not the best you could do if you trained on each individual data set, but this is the best you could do if you've never seen these other data sets. And throughout a large number of different data sets, there is sort of a gap between anywhere sort of 2 to 5 points, right? And so now we're getting into a mode where we can start to use label or use semantic classes of data sets that we have never seen, never reasoned about, and still do very well on them, right? And so that's why I think this is sort of the end of the semantic category. It's not the end of labels. We'll still use plenty of labels across all different data sets, but language models gave us a very cheap way to move into a more open world recognition, where classes are no longer these fixed size feature vectors, but classes are word embeddings. They are embeddings that are given by a language model. And if you want something else that you might not have had annotations for, the language model is hopefully able to interpolate to this new class, right? Now, this was the first part. This is the first big change. I think the second big change, which I actually like a lot more, is the move to transformers, which is transformers give us a way to think about our architecture, to think about our vision models in a very different way. And to sort of explain this, the way I was taught deep learning and the way sort of I was thinking about deep networks for the longest time was, well, you're given an input image. This is some grid of pixels, and then you have layers after layers that transform this into some feature map. I should use a different color here. All right. Then you have some more layers, and it transforms it again into a feature map. Yes, we were always able to change the size of this feature map. We're always able to sort of maybe increase and decrease the number of channels. But at the end of the day, sort of the only operation that we had that sort of did something interesting to this feature map was pooling, which was it took this feature map and it made it into a single vector, right? Everything else was always just sort of this fixed size feature map. And transformers changed that, right? Now VITs don't, unfortunately, yet. So if you look at sort of the way VITs work, they still sort of have these layers, and it's still some sort of feature map here in the end with the same number of tokens. And that's because they mostly use self-attention. But what really changes is the way we use cross-attention. Because in cross-attention, we now have an operator that is able to take one feature map, or actually a set of features, then we take another set of features, and cross-attention will transform one set of features using the other set of features. And this is a really simple operation, but it's quite cool to wrap your head around this. All right, because for the first time in many, many years, we now have an operation that does not retain the same feature map. All right, we can use arbitrary features to transform arbitrary other features. And I'll show you in the remainder of this talk how this actually allows you to think about vision problems in a very different way. And we'll start with multi-view recognition. And so in multi-view recognition, Fisher already set this up very nicely, and I'll just recap this very briefly. We're given images from all around the vehicle. And in our case, what we want to do is we just want to produce a map and place these vehicles in 3D. All right, so this is sort of the ego vehicle is somewhere down here. These are the different views. All around the vehicle. All right, well, there's actually 6, but and now we just want to infer all the 3D geometry from these different cameras. Now each camera overlaps slightly. So if you look at these two cameras, they have a minor overlap. This one here overlaps with the one over here, and so on. Right? So there's a slight overlap, but it's not quite enough to do stereo. Right? And so the way networks sort of dealt with 3D vision before, the most performant networks dealt with 3D vision was, well, let's do monocular depth estimation on each of these frames, right? So we'll do monodepth, and then we project it out to 3D. We'll do a bunch of complicated geometry to figure out where they end up. And then we're going to just splat things onto the map. And so if I draw a 2D example of how this looks like, so you have some camera up here on the car. Now we have a depth estimate. We split it out to onto the scene, and then we just projected this point onto the map. All right. So that's how sort of traditional approaches work. And it's not quite end-to-end because the splatting is actually quite hard to make differentiable. And it also sort of causes issues. What if you have these overlapping parts here, and the depth estimate is not quite consistent? You now have sort of overlapping projections, or what's going on, right? Now, let's take the same principle and just flip it around real quick. And so what we're going to do is we're again going to have the vehicle. we're again going to have the camera up here, and we're going to have a map down there. But instead of trying to go from the image onto the map, let's see how it looks like if we want to go from the map back into the image. All right. So if we start out from the map, and if I told you, hey, this point on the map is a certain distance above ground, right? There's again a geometric mapping back into the image. So we can go from here and project it back into the image. So not much happened. Like instead of doing monodept, we now assume we knew the height above ground and project back. All right. Now, if you tease apart this operation, well, what does this do? We're going to have some feature that tells us the height above ground. And then we'll have some feature or some projection operator that will help us figure out where in the camera this ends up in. We have some information in the camera, which is the color pixels or some feature that corresponds to the color pixels. And then what we're going to do is we're going to take this back out. It turns out this is actually exactly the definition of what a cross-attention layer does, right? We have some information here. And for those of you who are into the jargon, we have some query here. We have some key and value here. And so the query is just the information about, let's say, how high above ground things are. The key is sort of information how it would project into the camera from this angle. And then the value is just what the pixel value is in this color image, right? Now, the cool thing about this is we can now forget everything we learned ever about geometry. We can just make sure that the positional embedding of the keys and the queries have the necessary information to learn about geometry and hit the training button, all right? And now we can build sort of this end-to-end differentiable network that is able to learn all the geometric stuff inside of its instead of its cross-attention layers. All right. The only thing we need to make sure is that there is positional embeddings here that will give us the right information for the transformer to do projections. Now it turns out this will learn some amount of geometry, but it will actually look a lot more at color. So it will learn to map colors or sort of different appearance regions between the map and the image itself at roughly the right location. Right? And so now we could just, through cross-attention, we can take geometry and just learn it. Now this works quite well. It sort of matches the state of the art in 3D vehicle detection, or the state of the art at the time. The really nice thing is it is much faster. Since it's just, I think we use 2 layers of transformers or 3 layers of transformers, this is a very quick operator. We no longer need to do geometry and reproject, and we can get away with much smaller networks. Right? It also works well on estimating drivable area, and here we see a little bit of a boost. Here are some examples. So what I'll show you here is the video with the different views, and then I'm just showing drivable area in this video, and you see it sort of slowly build up. The build-up is nothing that has nothing to do with cross-attention or transformers. The build-up is really just the running average using the ground truth location. Here's another example. And again, this is all just geometry, and all this is just learned from ground truth sort of image and map pairs. All right, now we can also apply the same idea to tracking. And so Fisher already set up the tracking problem really well. And so just to recap, tracking aims to sort of detect and then link up objects through multiple frames in the video. Now, classical detectors do this sort of frame by frame, and a very popular paradigm is tracking by detection, or sort of joint tracking and detection, where frame by frame you detect objects and then you associate them, usually to the previous frame, or sometimes also sort of 2 frames further back if there's no good match in the previous frame. All right. And so this is really sort of a process that goes frame by frame by frame back. Right? Now, this is not quite how we would do tracking. You wouldn't ask you don't ask yourself, hey, is this the same person as this in the previous frame? And is this the same person as this? Like what most people actually would do is some global association, right? You would just say, well, okay, well, this person here, they're all the same. This other person here, well, they're all the same, right? And then the car is the same. Now, if I draw it this way, does anybody already see cross attention here? Right? If I told you the number of objects that I would expect, there is a way to express this as cross attention, where you have some query go in here, right? And that query attends to all the boxes, right? And then it gathers the information back. And again, this is an operation that we couldn't really express using our previous tools, but with cross attention, we can all of a sudden trace the global tracking problem, grouping all objects together into one in a very, very simple manner. And just to sort of drive this point home, what global tracking transformers do is you have a bunch of queries here, then you have cross attention between all the boxes and the queries. And you do this throughout all the frames. Actually, the arrow here is wrong. This is the same queries should attend to here. All images. And then we do this a couple of times, right? So we have a query, and each query specializes in detecting a separate group of objects. And so this is the way we can sort of get global tracking just with a bunch of cross attention layers. Now, we actually only need 2 cross attention layers and then half of a cross attention layer to do the grouping. And this is super simple. So we can now take global tracking, which is thought to be previously just actually fairly complicated optimization problem, and just express it with a few layers of cross attention. And the cool thing about this is sort of, if you put this on top of a detector, this takes less than 1% of the computational budget of detection. This is super fast. You're just going to run a bunch of cross attentions on top of your detectors, and you get tracking. The other way to think about this is actually, this is almost like, if you guys are familiar with DETR, this is a DETR style detector for tracks, right? All right, and here are some results. So this is the previous tracker. This is sort of a frame by frame tracker. And every time the color changes, you can see it lost track and it had to reassociate the object. Now, if you look at our results, yes, it lost the box once or twice, but the dog is almost always recognized as the same instance. And this is really only possible because we look at a much larger extent of frames and we group these things together globally. All right, it also works quite well in the tau data set. And sort of compared to prior methods, it's at the time of publication actually performed quite a bit better. All right, now the final thing I want to mention is we can also put large language models and the power of all of these cross attentions together into a very different sort of model. And here, this is actually the only thing I have that's somewhat relevant to driving, which is here we're going to look at how can we produce sort of traffic layouts and motion predictions or even policies that sort of follow a certain language description. And so the reason why you would want this is if you have a simulator that can simulate all sorts of traffic, it's very hard to generate very exciting and interesting traffic scenes. And so we have a model that can now sort of go from a language description, maybe from a language description of an accident or for something that you would want to control. You can go from this language description to to sort of a nice, interesting scene that you could test your vehicle on. And it combines the power of these language models with a very nice query-based, almost like a detector, but it's actually a generator for different trajectories. And the language model here, we use in context learning to take a text description and translate it into a structured representation. And you can even train these sort of large language models in context to produce descriptions with an arbitrary number of vehicles. Right, and so for each vehicle, it will tell you, well, this vehicle should maybe be on the right, on the left, on top. It should go fast. It should go slow. And you can sort of, with in context learning, you can learn a structured representation that captures all of this. You can also learn a description of what map you would expect. How many lanes would you expect? Sort of where would you want to where would you want the lanes to go? Is it an intersection, not an intersection? And we can use this in a very simple retrieval system that just checks for these attributes. All right. And once we have that, once we have a map and sort of this structured representation of traffic, we can go and build, similar to the detector or to the tracker I showed you before, we can build sort of a cross-attention based model that will go and produce interesting traffic scenes. And so we'll start with a description of every agent in the scene. And the description is the structured representation that the language model gives us. On the other hand, we also have a representation of the map in vectorized form. Then we're going to encode this map. We have some map features, and we'll use these map features in a cross-attention layer to update what we think each agent should do conditioned on that map. And so the cross-attention really comes in this generative transformer here. Then we're gonna sort of from these features, we're gonna decode their motion. We're gonna decode their attributes, which is how big they are, how small they are, and a couple of others. And then we will go back into the map and figure out where we should place each individual agent. And here there's another cross attention here, which essentially we assign each agent a positional embedding, or we produce a positional embedding from each agent, and then the map itself produces positional embeddings, and we'll use this cross attention to sort of snap agents to different locations on the map, right? So this is really truly embracing like sort of the flexibility you get if you have lots of sort of interesting cross attention operators. And the results are pretty cool. So you can have a text description like vehicle 1 is traveling east in the left turn lane and attempts to turn left when it collides with vehicle 2 traveling west in the left through lane. Right? And this is what it produces. Right? And again, it retrieved the right map for this. It placed the vehicles and it produced the vehicle's dynamics properly. Here's another example. Vehicle 1 approaches an intersection and does not notice stopped vehicle ahead. Vehicle 1 strikes the rear of vehicle 2. Now, this is not quite an intersection, but you can imagine maybe on top there is going to be an intersection. And actually, the fact that the lane splits probably indicates that there will be an intersection later. Right. Here's another one. Vehicle 1 and vehicle 2 collide at an intersection of 2 urban traffic ways, with vehicle 1 striking the left side of vehicle 2. I didn't quite get the left side here, but it got the striking. The ego car here is I think it's the red car in this, turns right. Most cars are moving in slow speeds. Now we also tested this in actual crash reports. So NHTSA has a large data set of real crash reports, and we wanted to see, well, can we reproduce these crash reports? And so for some of these crash reports, they even have like beautiful diagrams. And we sort of just wanted to see, well, can we produce traffic scenes that would follow these reports? And it turns out we can pretty well. We have an archive that's going to come out soon, and we'll sort of show sort of human evaluations in there, and we can get to about 90% of the scenarios we can reproduce. But what I will show you instead is we can also put this directly into a simulator. And so this is metadrive, and we can try to test policies that were developed for these simulators on the scenarios that we generated. All right, so these are two different kinds of policies, IDM and PPO. Here's some more examples. And so maybe to wrap up, what I'm really excited about is really the fact that everything is sort of changing. We can do many more things. We have language models at our disposal that sort of are the end of categories. We can use them to start to sort of as a useful input to our models. And then we also have much more flexible architectures now. It's no longer transform activation map into another activation map. It's really anything you would want to do, you could now express in a model that you can differentiate through and learn. Right? Yeah, with that, I have one more announcement. I mentioned I'm splitting my time between Apple and UT. All the work there was done at UT. We also hiring postdocs at Apple. So if you're interested, just shoot me an email. And with that, I'm happy to take questions.
Thank you very much. Questions, anybody?
Hi, first of all, thank you for your talk. I have two questions. First question is about DETIC, your work on last year on ECTV. So my question is, extending to open vocabulary is very interesting topic. And in your DETIC, you use ImageNet to expand the vocabulary. And my question is, what's the performance boost from the increase in seeing classes or increase in samples? That's my first question. And second question is about the cross attention. Cross attention is is known to be powerful. But my question is, maybe for short videos it may be okay, but for like streaming settings or like videos that can last hours or so, then have you considered like the space memory time complexity of the? Yeah, those are my two questions.
Okay, good. Yeah, so the first question, the trade-off between number of classes or number of annotations that we have and just the number of classes we have, it's pretty hard to quantify, and I don't think we have studied this enough. Now for the second question on, yes, cross attention is actually really slow if you have long videos. We have some work at ECCV last year where we looked at if you reformulate the kernel in cross attention the right way, you can actually make it streaming. So you can sort of have a cross attention operator that will add elements to a queue or even just computer running average. And that one sort of does not scale with the length of the video. So you can just run it and it will not become slower. So you can just build up longer and longer sort of memory.
Okay, so first question, you're not too sure?
I don't know. We would have to do the experiment for the first one.
Thank you
Yes.
so much.
Yeah. Yes. Fisher will return favor.
Okay. It's very interesting talk like pointing out the behavior change going through computer vision. I have a question on one of the part. So it's very interesting that you can expand the detection to 20,000 categories. So what do you think will be needed in order to expand this to everything we can make? Well, one thing we already have is we have a lot of this, like this, say a lot of data to increase where we have the caption and image pair.
Yeah. So like, okay. So everything we can name, there's really two categories I would split things in. Every noun, I think we're very close. Like we already trained on captioning data. Every adjective, that might take a little more time. Every verb, I have no idea. I think like English language is actually quite poor in describing actions and sort of verbs. And so I think there we're going to hit a wall eventually. We can express way more visually at some point if we talk about actions and the way like states change than we can with language. And so there, I don't know how to get there. In terms of sort of adjectives and nouns, I think will probably, the data that we have might get us close, and then otherwise generative models might get us over the hump.
It's interesting to go from that work that's kind of better than I thought.
Yeah.
I have a question on the queries for your detection as you're tracking.
Yeah.
So it's kind of like the learning queries like in the DTR, right? So what exactly is the learning queries? What are they learning exactly? It's a grouping of some information which is basically a vector according to numbers. But do you have any insight on what exactly it is learning?
Yes, this is a very insightful question. And I totally glanced over this detail. So it turns out if you learn queries, a fixed set of queries, it doesn't actually work that well. And so the trick we play there is the queries in our global tracker are all the detections that we have in the last frame. So we look at all the detections that we have in the last frame and use those as queries to do the global association. And so that way we're always guaranteed to have tracks that sort of end at the current frame, and we'll detect all of these. We might not detect tracks that actually end a little bit earlier, but then we could sort of just shift back a little bit and
Just like a MLP transport features of the detection.
yes. We couldn't get the actual pure debtor style queries to work very well.
Final questions for the speaker? Okay, so let's thank you.
Thank you.